자, 우리 시작할게요. Okay, let's continue implementing sequential y8664. So you're gonna, as I said last time, we're gonna release homework number 3, which will be due after the midterm. So it'll be it's actually very long homework. It's usually due in 3 weeks. So we're gonna give you 3 weeks, but it's a lot of work. So please start early. I recommend. Okay, so let's get started. I think I stopped somewhere around here. So basically the idea was, we basically break down an instruction into multiple smaller pieces. So, basically we first identify what sub-operations are necessary to implement a single instruction. So in this case, let's say, in page 20, let's think about this conditional move as an example. So if you have a conditional move instruction, what you have to do is first you have to fetch the instruction. So you fetch is basically read this instruction from memory. And you extract those parts like I-code and I-fun, which specify that's actually opcode. So opcode of the instruction, which is what instruction is. And we also extract, depending on the instruction type, maybe it's depending on the opcode, we have to actually, in this case, we have to extract register identifier, so RA and RB, which is in the next byte, and also, we actually compute the next PC here, because in this case, the instruction word is actually 2 bytes. So in y86, as you know, it's like a variable length instruction. So in this case, we only have like 2 bytes for this instruction. So next PC is computed in this stage. Val P is PC plus 2. In decode stage, we read the register. So in this case, we only need to read one register here, like RA, because this is conditional move, so that if the condition is satisfied, we actually do move from source to destination. Otherwise, we simply replace it with NOP. Don't do anything. So we actually read the register RA here. In the following stage, we pass the value of A through ALU. So that means, in this case, val B is 0, right? So this one is basically as good as nothing. It's just. So val E is actually equal to val A, which was the value of register RA. And in execute stage, we selectively override the destination register specifier. So in other words, in this case, we check, because it's conditional move, we have to check the conditional code and the suffix of the instruction. For example, maybe this one could be C move E or C move GE or something like that. This is a suffix. So depending on the suffix, we actually have to check whether that condition is satisfied or not, by reading the conditional code. So if this condition is satisfied, is not satisfied, then we override the destination register to F. Okay, so what does it do? So originally we are supposed to write the value to the destination register, because we are doing move, right? But if the condition is not satisfied, then actually we change the destination register to F. So F is basically no register, right? We are not writing to any. Okay, so it's basically effectively disable register update. And in memory stage, we don't do anything, do nothing. In write back stage, actually we write the value of E to register B. That's what's happening in write back stage. Okay, and finally in the PC update, we overwrite the PC register with val P. Actually, this change will be reflected at the rising edge of the next rising edge of the clock, right? Because PC is the register, so this combinational logic, so that the value gets updated only at the rising edge of the clock, right? So that's what's happening. All right, so let's do a few more things. Jump, how we can implement jump. We do the same exercise for this instruction. So if you see the jump instruction, in high level, we can break down this jump instruction into following steps. First, in the fetch stage, we read 9 bytes, right? Because jump instruction consists of opcode plus 8-byte address, the target address, right? So it's actually 9-byte instruction. So we increment the PC by 9. And decode stage, we do nothing, because this jump instruction doesn't require any register, right? It just is You don't have to read register here. So you can simply, do nothing. And in execute stage, you have to determine whether to take the branch based on the jump condition and the conditional code. It's actually the same thing as in the condition remove, because depending on the value of this suffix, because it's JX, this is a suffix, right? This one could be JE, or this one could be JGE, or something like that. This is suffix. Depending on suffix, certain condition must be satisfied for this branch to be taken. So you actually look at both this like a suffix and the current value of the conditional code to determine whether this condition is satisfied or not, right? So if depending on the jump condition and conditional code, you actually have to determine, and in execute stage, you determine whether to take the branch or not. In memory stage, in write back stage, do nothing. In PC update stage, you basically overwrite the value of PC with the correct target address. It'll be either the target address within the instruction or the just next instruction, depending on the condition, right? So that's what's happening. So here, we also do the same thing. I mean, stage breakdown. So first, in the jump case, in the fetch stage, we extract opcode, and also we extract the target address, which is val C. So this is the destination address, and val P is basically a fall-through address, because we compute two different address, because it could be either val C or val P depending on the condition. So we actually calculate the target address for both, whether it's going to taken or not taken. It's taken, then this one will be the target. If it's taken, if it's not taken, then this one will be the target address. So we compute the both target addresses. Decode stage, do nothing. In execute stage, you evaluate the condition. So if condition is basically it's one bit flag whether the jump condition is satisfied or not. So this one is like a Boolean variable, CND, the Boolean variable. If it's true, then it's taken. If it's false, then it's not taken. So memory stage, we do nothing. In write back stage, do nothing. And finally, in PC update stage, that's what's happening. So if the condition is true, then we take the value from this val C. Otherwise, we're going to take value from val P. So that's basically how we select the value depending on the condition. And we're going to update the PC based on this expression, right? By the way, I read this like a midterm, course evaluation from some of you. Actually, 6 people, wrote the course evaluation. And some people actually said I'm a little bit too fast when you give a lecture. So, well, yeah, sometimes I do. So maybe it'll be really helpful if you ask a question, or or you can give me some sign to slow me down. That would actually be very helpful. Please, if I say sometimes speak too fast or gloss over something, maybe please raise your hand or ask questions, or just let me know. Then I can hopefully slow down a little bit. Also, another thing I would recommend is we actually have recitation session, because some of you actually don't have like a strong background in this area, and maybe you actually need like more time to understand and digest the material. So in that case, please show up and Friday because TAs are very capable people. They are very well versed in this area. So they can actually help you a lot. So if you maybe it's too fast, then maybe you come back on Friday, or using Kakao or something, so that that way hopefully it actually helps you address these issues a little bit at least. Okay, so let's move on. So next instruction is call. So we do the same thing again and again. By now, why are we doing the same thing again and again? But that's actually the goal. I mean, because I want to show you, even though we actually cover different instructions, they actually more or less go in steps, right? That's what I want to. That's the message I want to convey to you. So let's say executing call instruction, what it takes to execute the call. So in fetch instruction, we read 9 bytes and increment PC by 9, And decode stage, no need to actually we have to read register here because in call instruction we first have to push the return address to the stack, right? That's what needs to be done. So in decode stage, we read stack pointer like RSP, the RSP register. Okay, and in execute stage, we decrement stack pointer by 8 because we want to push a new entry, which is return address. And pushing means you actually the stack grows downward. So if you want to push an entry, you have to decrement the stack pointer by 8. In memory stage, we write the incremented PC to new value of the stack pointer. So thing is like, let's say your previous stack looks like was like this. Let's say it was stack, and originally the value was here. Stack pointer was stack, pointing to this entry. But if you execute a call instruction, it first allocate a new quad word like this, and then the stack pointer moves to here like this, right? And then you write the incremented PC. The incremented PC is basically a return address, right? So what I mean by incremented PC is the next instruction, right? The current instruction is PC pointed to by PC, and PC plus in this case 9, right? Because call instruction takes 9 bytes. So the next instruction will be PC plus 9. So this one is like a PC plus 9, right? So actually push that value, write this value into the stack here. This one, PC plus 9, will go here, right? It's actually happening in memory stage. In the write back stage, we update the stack pointer because we decrement the stack. We actually calculate the value of a new value by RSP here, which will be written back into the register file in write back stage. Finally, in the PC update stage, we set the PC to the destination. The destination is here, right? We jump to the target, the function, right? So that's what's happening. So here's stage computation again. In the fetch stage, we extract opcode and read the target address from PC plus 1. And the new PC value will be PC plus 9 because we compute the return point. This is the next instruction, right? The next instruction is also the return address after the call. In decode stage, we read a stack pointer, and let's call it val b. In execute stage, we decrement stack pointer, so it's val b minus 8. So this one is called val e, let's say. And in memory stage, we update the value of at the location val e. This is the address, right? This is new, the newly allocated like a stack address. We write val p to that address. And in write back stage, we update the stack pointer. In the PC case, we update the value of PC with the destination. Finally, the return instruction. So return is kind of the opposite to call. So let's say you return from the function, and it takes only single like 1 byte, right? So we fetch just 1 byte, and in decode stage we read a stack pointer. In execute stage, we increment the stack pointer by 8 because that will be the new stack pointer. And in memory stage, we read the return address from the old stack pointer before we increment the value by 8. So basically there are two, let's say in the previous figure, if you remember, let's say this one. So here, when you actually call the function, the stack pointer actually points to this like a red arrow. Let's say this is red. Red arrow, this is the current stack pointer, right? When return instruction is executed. So first of all, you actually also calculate this RSP plus 8 because you need to pop this like return address, right? So, but actually you have to read the return address from the old value of RSP, right? So what's happening in here is you actually read from RSP, and this one actually calculates RSP plus 8 because this one will be the new stack pointer after you pop it, right? So this value will be you update the stack pointer with this value in the write back stage, but still you have to read the return address from the old value of RSP before you increment it by 8, right? So you have to distinguish the two values. Actually, you read the value from RSP, but you will update the value of RSP to RSP plus 8 after you're executing read instruction, return. And PC update, you save the PC to the return address. Basically, you read return address from here, and that value will be used as, the value for the next PC. Okay. So finally, the read, like a return. You first read like 1 byte from fetch stage. In decode stage, you read like a stack pointer, and increment the stack pointer by 8 in execute stage. But you read the return address from the old value of RSP, right? Because RSP is here. So this one's basically old address, old like value of stack pointer before you increment it by 8. But you use val e in write back stage because you need to use this value to update the value of RSP. Okay. Finally, in write back stage, you simply update the value with val m, what's read from the memory, because the return address is placed in the stack, so you have to read it and use it for next PC. So here is the summary. Basically, what if you actually take the union of all these like steps we have looked at? Because we have seen for different like instructions, very common, but a little bit different from instruction to instruction, right? So we actually have very common like a set of instruction, a set of like steps, and let's say you take the union. I mean, you basically put them all together, union of all these like steps we have seen. Then this is the union of operation we actually have seen in this case, right? But what's happening is, depending on the instruction, we do like mix and match with different sub-steps to execute some instruction. That's what we want to do. So the idea is, we make basically hardware for all of these like unions, all these like sub-operation we have seen. Basically, we make the hardware for all these like sub-steps. But when we actually execute an instruction, we activate only part of like a subset of these operations to implement the instruction, right? So that's what you want to do. So this one is the union. I mean, this is all of the operation we have seen, in executing all these instructions in y86-64. And let's see, which parts, which subset is actually activated for individual instruction. So let's think about this OPQ instruction first, like OPQ. Then this one actually activates reading the instruction like opcode and reading this register byte. But this one actually doesn't activate this read constant word, because some instruction like call or jump or those instructions actually also require the next like a constant field, right? In that case, this like a part will be also activated, but in this like a up X instruction, you don't really need it, right? Because you don't really need like any constant field for this instruction. So this value is not activated. And the val p is to in decode stage it read like both R and RB register. In execute stage you do calculate val e and set the condition code here. And in val m in memory stage we do nothing here. It's basically we don't activate like this one. Also in write back stage we only have like one register to be updated. So we only update this register value using val e. But there are some just one case you need to update like two registers at the same time. What is the instruction that update the two registers within single instruction? What is that? Remember? Which instruction actually execute two registers at the same time? 다음 주 시험인데. So in pop instruction, you actually need to update the value of the register as a result of pop, and also you need to update the value of RSP as a side effect, right? So the pop instruction is the only one which update two registers at the same time. Okay, and the PC update, PC will be val P. So the point is, you know, all instructions actually follow more or less the same, like a general, like a pattern, but you know they actually differ in what gets computed on each step and which parts will be activated and which parts are not. Okay. So let's think about another instruction, call. So in this case, in fetch stage, we read opcode and also calculate the val C here. In this case, val C is activated because you need to read the constant value, the call like a target address. And val P is updated with PC plus 9. And in this case, you need only like one register to read, so step pointer. And in execute stage, you compute the val E using val B register -8 because always decrement this step pointer by 8 to push the return address. In memory stage, you read. You actually write, basically push this like a return address to the stack, so you write to the memory. And in write back stage, you update the stack pointer, and finally you update the PC. Okay. So let's think about what are those like computed values to implement this. Let's think about you write some like a logic to implement this like a logic circuit. So because you have already taken the logic design course, let's think about let's say you write some Verilog code to actually implement this like a processor. That's what we want to do. But we are not using like a Verilog. We actually use like a much simpler C-like HCL, like much simpler language. But the idea is more or less the same. So there are some like computed values here. We first need to derive like icode, ifun. Those variables mean like instruction code and instruction function, like opcode. And RA and RB, like they are like a register specifiers. RA, which register to read, register A and register B. Val C is the instruction constant. Some instruction actually have constant filled, and that's like called val C. And val P is incremented PC. Basically you increment the PC value by the length of the instruction, which actually point to the next instruction, right? That's the val P. So we define a bunch of variables that indicate like a specific, that actually take a specific value depending on the instruction. In decode stage, we actually have like other variables, like a source A, source B. Those are like register ID for the first operand A, and the second one is register ID for the second like a register operand. Destination E, destination M is basically when you actually sometimes you need to update the register value either 1 or 0 or 1 or 2, right? As I said, in case of a pop instruction, you need to actually update 2 registers. So we actually need like a 2 write port, right? Because you need to update 2 registers at the same time. And so this is called like a dest E and dest M because sometimes the write back value comes from execute stage. For example, if you actually have like an add instruction, the value to write back to the register is actually coming from the execute stage from ALU, right? But in case of like pop instruction or like maybe some like a move instruction from memory, then this like a value to write back to the register is actually coming from the memory stage, right? From the output of the memory, right? So in that case, so there are 2 different choices where this value to write back is coming from, and the E means like from like execute stage, like from the ALU. In case of M, that means the value is actually coming from memory stage, like from the memory out data memory. And register value AB will be the the value you read from the register file, A and B. In execute stage, val E is ALU result, the output of the ALU. CND is move branch or move flag. So CND is basically one bit like a true, false, like a Boolean flag. If it's true, then the condition is satisfied. If it's not true, then the condition is not satisfied. In val m, this is value from memory, which switches the output from this like a data memory. Maybe it'll be more, this like meaning of all of these things will become more evident once you see this like a schematic. So this is a simple like a processor, like a single, like a sequential processor we want to implement. As I said, in this lecture, all instructions take just one cycle. Okay, every clock cycle, every rising edge of the clock, you read a new instruction and execute that instruction within a cycle. And then in the next cycle, you read a new instruction, and then you execute that instruction during the cycle. In the following cycle, you read like a new instruction again, and then you execute that instruction during the cycle, and so on. So it's basically one cycle at a time model. So only execute one instruction at a time. But in the next lecture, we're going to introduce what is called pipelined version of the processor. In that case, you execute multiple instructions at the same time in overlapped manner. So that's what we're going to cover next time. But this one will serve as a baseline. So this one will be the one instruction at a time. One instruction at a time. That is like one instruction per cycle, clock cycle. That's what we are doing. So here is a processor, we are designing. You can think about this like boxes as, module. So if you have ever written any code in Verilog or like some hardware description language, module, right? You actually define some module, actually defines input and output ports, and then you describe the behavior, input-output behavior inside the module, and so on, right? So you can think of it like individual these like boxes, like a blue box and gray box as module, like a Verilog module. Okay. So here, blue boxes are pre-designed hardware blocks, like a data memory. We already introduced how the data memory, how memory works, like during the last lecture. And this is ALU. We also covered ALU, how ALU works, like during logic design, lecture last time. And this is conditional code register, CC register, because it actually holds what's the current status of the conditions. We actually have a zero flag, carry flag, and overflow, and so on, right? We actually had like 3 flags here. And register file, we also covered how register file works. So as you see, in register file, we have 2 read ports, which is labeled A and B, and 2 write ports, M and E, right? That means, this register file can read like 2 registers, up to like 2 registers in a single cycle. And this register can also, we can also write up to like 2 registers within a single cycle. So that's the reason why we actually have 2 read ports and 2 write ports. And those gray boxes, okay. So by the way, this instruction memory is also like the same internally same as like a data memory, but now we assume like a separate like a memory structure for data and instruction. And PC increment is, you can think of it as a PC register. So this is register. Okay. Also, let's say we actually have gray boxes. Gray boxes actually is a control logic. So we're going to go over this control logic in more details in a later slide. And for example, let's think about this box, like ALU func. So what this one does is, depending on the instruction type, we actually have to configure this ALU correctly, right? So if, let's say, ALU can, do a bunch of different things, like actually 4 different things, like add, sub, XOR, what is that last one, AND. So we can actually you can do actually 4 different operations in ALU, and depending on what's the instruction you're executing, you actually have this, configure this ALU correctly. And this like gray box is responsible for generating the correct like a selection signal depending on the instruction type, right? If the instruction is XOR, then you actually need to do XOR. And if your instruction is like an AND or like something actually, or like even like a call instruction, that you need to do like addition with this LRU. So that kind of control is done by this like gray box. And white ovals, like a label for signal, those white ovals are not really real concrete like a hardware block, but this is kind of a label for some signal. You can think of it as like a wire in Verilog. If you have written any like Verilog code, there is some like construct called wire. And wire is not really, it's just line, right? It's not really any like concrete like a logic or anything like that, but it's like it's kind of metal wire, like a line, right? Connecting these 2 points of circuit, right? So you can think of it as a wire, name of the wire. It's like white ovals. And thick lines, 64-bit word lines, and thin lines, 4 to 8-bit values, and dotted line is just 1-bit value. That's the convention. So thick line is 64 bits, thin line is 4 through 8 bits, and dotted line is just 1 bit. All right. So let's take a look at those things in more detail. So fetch logic. Let's start with fetch logic. So there are pre-defined blocks. PC. PC is a register that actually contains containing PC, and the instruction memory. So instruction memory read like 10 byte, because our instruction is like as long as can be like as long as 10 bytes, somewhere between 1 and 10, right? The shortest instruction is like 1, and longest instruction will be 10. But in this case, we assume the worst case. We read like a 10 byte anyway, and then depending on the instruction type, we only used subset of this like 10 bytes. That's the idea. So let's say PC is the input to the instruction memory, and this we actually read like a 10 byte from this instruction memory, and also there's like an IMEM error signal, which is if you actually request like some invalid like address, let's say out of range, maybe you request some like a address range which is not covered by this memory, then this like IMEM error will be asserted, will become true. And this like split box is actually dividing instruction byte into ICode and IFUN. So if you read the byte 0 is actually is the opcode, right? What is called opcode. And we divide this like opcode into 2 pieces, like two 4-bit pieces. And the first one is like ICode, and second one is IFUN, right? So this like split does nothing. It does nothing, but just simply grouping the wire, because you read like 8-bit data, then you name the first 4 bit as ICON, and the second one is IFUN, right? So that's what this split box does. And align actually does the similar thing. So you actually read the next 9 bytes, and then split those wires into 3 groups, maybe more than 3 groups. RA, RB, and vel C. Depending on the instruction type, you may need this a register specifier, RA and RB, and also you may need this vel C, which follows this opcode and register specifier. So you basically what this block does is you actually extract those fields from the instruction 10 byte of instruction you read. That's what this part does. And what this PC increment does is, this one, let's actually execute it. So PC increment, basically it computes the next address, next PC address, which is the sum of the current PC and the length of the current instruction, right? So if it's like a move instruction, then the vel P will be PC plus 2. If it was let's say it was call instruction, then it will be PC plus 9, because call instruction actually has only opcode plus 8-bit of target address, right? It's 9 byte in total. So vel P will be basically the starting address of the next instruction. which is computed by this this PC increment block. Okay. And let's think about this control logic. So so there's some like a control logic like these gray boxes. So here, this instruction valid is basically you parse this like I code and whether this like I code is valid or not. So if it's valid, then it's true. If it's not valid, it's false. So let's say you read a new instruction, and then the opcode was, let's say, F. But F is not really defined, if you remember. I don't know. In this case, here there's no instruction starting with F, right? So if it's if you read this like I code, and if the value were F, then now you assert invalid instruction, right? Then that will be actually captured by the control logic, and it will actually set the status register correctly. So yep. So and the next one is I code and ifun. If the address was invalid, then actually we need to override this I code and ifun to like a NOP, like a no operation. So again, if you go back, this one is NOP, like a no operation. So this one is kind of harmless. I mean, if you execute, it just do nothing, right? So if you actually hit upon like some invalid like an address, then actually the control logic replace this instruction with NOP automatically. So that's what this like blocks do. And need reg ID is this is actually generates like a 1-bit flag whether this instruction requires register or not. So this one actually takes this like these two, you see this I code as input and generate 1-bit output, which is whether this instruction requires register specifiers or not. Okay, and this part like a need val C, this one also takes this I code as input and generate 1-bit signal, which specifies whether this instruction has a constant word or not. Okay. So let's see how this one is actually written in HCL. So let's think about this part, I code, and I found this block, these two blocks, how these two blocks are written, the control logic. So as I said, the I code, if IMEM error happens, this is IMEM error. So IMEM error is basically you try to access some like invalid address space, right? So if you try to access some invalid like address, then it will actually override the I code to like a NOP opcode for NOP. INOP is basically the NOP code, the opcode for NOP. So in this case, to be concrete, this INOP is constant value of 1. Okay, so this is like a macro. So this one is this value. This is like actually the constant value 1 because the NOP is like 1, 0, right? And if the same thing happens, if IMEM error happens, then it will actually override the value to F none, which is 0. I mean, 1, 0 is basically like a NOP, right? No operation. Otherwise, simply you pass through what you read from this memory. Okay, that's what's happening. 여기서 얘가 하는 거는 순수하게 잘못된 어드레스를 만약에 읽었으면은 그냥 명령어를 동적으로 노브로 바꿔주는 거고, 만약에 그게 그냥 아니면 원래 있던 명령을 그냥 읽은 명령어를 그냥 그러니까 업코드를 그냥 패스해 주는 거죠. 그냥 그대로 전달해 주는 거죠. So if IMEM error happens, this like instruction will be dynamically overridden to become NOP. Otherwise, you simply pass the whatever opcode you read from memory. So let's think about the other two boxes here. If you see in two slides ago, there are two boxes here. Both actually take this I code as input, generate like a 1-bit flag as output. Okay, then how we can actually describe the functionality of these two blocks. So the first like a need reg ID is true if the I code, the I code I read from memory is either like RR move OPQ, push Q, pop Q, IR move, RM move, or MR move. If you see this like instruction format, which instruction actually require register specifiers? So if you see, this conditional move, IR move, RM move, MR move, OPQ, pop Q, and there are two pop Qs. Push Q and pop Q, right? Sorry, this one of these is push. So only like those like a check mark like instructions actually require register specifier. So this one actually generates 1-bit output, which becomes true if the instruction is either one of these instructions. Okay. Likewise, if the instruction valid signal, so instruction valid signal is whether this is really like a valid instruction or not. So this one becomes true if instruction code is one of the following. If all of these like instructions that are defined. So in this case, INOP is INOP is like a macro for constant value 1. This constant value 1. IHalt is macro for constant value 0. IR move is like a macro for constant value. IR move is 2. This one will be 3. This one is 4. Up to the last one is actually B. Right? So you can actually translate this like a line into like as follows. If the I code is somewhere between 0 and B, then your instruction is valid. This one will be true. Otherwise, this output will be false. Right? Because we don't define any instruction starting with C or D or E or F. Okay? All right. Let's move on to decode logic. The second part, like decode logic, looks like this on your right. So at the center, we actually have register file. And as I said, this register file actually has 4 ports, 2 read ports and 2 write ports. So we can read up to 2 registers at the same time, and we can write to up to 2 registers at the same time. Okay? There are 4, control logic, which actually computes the register specifier. Because we actually have 4 like register ports. Each port actually require, the address for the register ID, right? For read or write. So there are 2 read ports A and B, write ports E and M, and addresses are register IDs or 15 because we have like 15 registers 0 through F, right? We have 15 registers 0 through E, and F is reserved for special purpose, which is like a no register, no access. And control logic, there are 4 like control logics blocks: source A, source B, read port addresses, and dest E, dest M, like a write port addresses. There are 4 like logic blocks. 4 control logic blocks. And signal is like let's say condition. C and D is the condition indicate whether or not to perform conditional move. This is actually computed in execute stage. I'm going to introduce later. But let's say this one actually takes one signal as input from execute stage. Okay. Then let's see how we can actually compute like all of this, derive this signal, source A, source B, dest T, dest M, dest M. So let's start with source A, the first register specifier, source A. So these are all all like an instruction that requires a value from the read port A, the first read port. So here, for example, in OPQ instruction, like add Q, something like add Q, we actually have to read value of RA through like a source A. And in case of C move, we actually have to read the value of RA to actually copy the value to register B, and so on. And all of these instructions basically requires read from register like source A, the first read port of the register file. And so if you see, which value will be read from the register file. So if you can actually control this source A, define the source A as follows. If the I code, let's say your instruction is either RR move, RM move, or OPQ or push Q. If your instruction is one of these four, what I circle, where's the last one? Oh, push Q is not here. Let's say there's another one, push Q. Push Q also needs to so in case of like, this is not pop Q, this is actually push Q, right? So in case of like a push Q or, if you have a push Q, this is actually true, pop Q, but in case of push Q, you also have to read the value from register A, right? Because you need to read from register and push it to the memory, right? So this push instruction is not here, but if your instruction code is either RR move, RM move, OPQ, or push Q, one of the four, then you have to read the value of RA, the first register specifier, right? You have to read the value from first register specifier. And if you actually have pop Q or return, then you actually have to read like this stack pointer from the first like a read port. Okay, and otherwise you don't really need to read register in this case. So that's basically how you define this source A combinational logic, which actually takes I code as input and generate what's the register ID you want to read from. That's basically what this source A block does. So in summary, depending on the instruction, you either read from register RA or stack pointer, depending on the instruction type. And second example is like a destination E, this is like a DSTE in the figure. So how we can determine the destination register for the instruction for like a register, for a write port E. So if you see those instructions, there are some like instructions that actually write the value from execute stage to the register file. Those examples include OPQ instruction, like add Q, sub Q. You actually have to write back the value to the register file. And C, like a move instruction, you have to write the value to the register. And pop Q instruction, then you actually have to update the stack pointer. And call instruction, return instruction, you actually also have to update the stack pointer. So this is called val E because the value to write is actually obtained at the end of the execute stage, like E stage, right? Without accessing memory. So in this case, you can actually also write this block control logic as follows. So that's the destination register ID for the destination register ID for execute the first like a write port, like a E port, is determined like if like conditioner code I code is RR move and the condition is satisfied, then the RB will be the register, the destination. And if the I code is IR move or like OPQ, then again like this RB will be the destination register. And finally, if the I code is either push Q, pop Q, call, or return, then the stack pointer will be the destination. Otherwise, don't write to any register. Okay.
I'm not really clear about the last slide. Is the push instruction. Is
You mean this like a, oh yeah, so we don't actually have push here, right?
Yeah, I mean, actually, push exists in the last slide, but right here, I got the same question. Like, we are popping through, but actually it only appears once.
Yeah, so, you know, because in case of a pop, I don't know whether I understood your question correctly or not, but in case of pop instruction, you have to write, like, update like two registers, right? Like, you know, the stack pointer and the value register, right? So this one actually only shows the one of them. I mean, there's the value part. No, actually, it's actually a stack pointer part. It only shows us the update of a stack pointer, but actually we also need to update the value too as a result of popping, right?
Yeah.
So this one actually is handled by DSTM, which is not shown here. So if you see in the figure, we only, you know, covering like this part. So there are two like write ports, right? E port and M ports, right? And, you know, we in the previous slide we only covered like a E port, but also there's like we didn't show it to you, but there's also like M port, which will actually, you know, for that like a port, we're gonna actually have this pop entry, which actually write the value to the register file.
So does it mean that the M port is only used for instructions like pop and push?
No, it's just for, it's omitted. I mean, it's just simply just, you know, because of, you know, time constraint and space constraint, we simply omit it. But we can actually do the same exercise as we did for this thing. Maybe you can add one more slide and like M destination, and we can also basically gather all the, like, you know, instruction which actually write the value through like an M port. And M port is actually meant for the value coming from the memory stage. So this one is meant for the value coming from execute stage, because, you know, stack pointer, the value of this new stack pointer is computed in like execute stage. But there are other values that are actually computed, actually read from this like a memory stage, and that value will be written back through like M port in the register file. You got it? All right. Any other questions? All right. So let's move on to the second, like a third stage, like an execute logic. So in the execute stage, we need a few things. Like, you know, there are also like a pre-built like a computational like a units, ALU, because we already covered ALU last time. So, you know, ALU it's like a Swiss Army knife of computation. So depending on how you configure it, it actually takes two like operands as input and generates one output operand. And, you know, depending on the configuration, you can add or sub or, you know, XOR or AND. You know, that's basically what ALU can do, arithmetic logical unit. And CC is basically conditional code. So this is a register with, you know, 3 condition code bits, like carry, overflow, and 0. In condition, this is, you know, computes, you know, the conditional jump and move flag. So this is kind of conditional logic. Basically, you know, we in the previous like several slides ago, we covered, you know, in conditional move, we actually have to compute by looking into both the suffix of instruction and the conditional code. We actually have to produce 1-bit signal called CND, which means whether this condition is satisfied or not, right? So this cont block is responsible for generating this CND signal, which actually takes, you know, conditional code and this XX thing, this instruction, there's a suffix, right? This XX suffix as input and generates like a 1-bit, like a true or false like a signal. This one actually it's a function generating this one is a true or false. Okay, so that's what this like a function is implemented by this cond box. So, and we also need several like control logic, like a combinational logic, which actually, you know, generate the control signal we need. You know, set CC signal is should this conditional code be loaded or not. Okay, so, you know, we generally as a result of computation, we need to update this conditional code. But other instruction maybe jump or or push, pop, all these things. They don't really need updating this this conditional code. So it's kind of depending on instruction type, we need or need not update this conditional code. On ALU A is input A to ALU, because there are several selections for the input to the ALU. And also ALU B is selecting the second input for the ALU. And ALU func is what function should be computed, like AND, or XOR, or like add what. This is actually determined by this conditional logic, this control logic. So let's think about this ALU A input first, this one. Here, this is basically all the cases we need to handle over different instructions. For example, if you have OPQ instruction, then the first input will be val A. And let's say if you have a RM move Q instruction, then the first input to ALU must be val C, and so on, right? And in case of this pop, push or pop, then you need to have different value. I mean the constant value. So there are different choices, different selections depending on different instructions. So you actually provide all these selections and then select one of them depending on the actual instruction type. So this is how we select the input signal, input value for the ALU, first input to the ALU. And if the instruction is either register move or OPQ, then we actually simply forward the value A to the input to the ALU. And if the instruction is either IR move, RM move, or MR move, in this case, we actually need to compute the address to access, right? So if you remember, it looks like we have to first calculate the sum of these D and D and RB, right? So we select this val C, which actually holds the constant value taken from the instruction. And if I code is either call or push, then this one will be constant value, -8, because we actually have to push some value into it, right? So in this case, the value will be -8. And if the instruction is either ret or pop Q, then the value will be positive, +8, because we need to pop one entry. So that's basically how we select the input value, the input A to the ALU. And what about operation? So in case of operation, it's relatively simple. If the instruction is OPQ, let's say this is not OPQ. So if the instruction was OPQ instruction, then basically we select whatever operation specified by the instruction. It'll be the add, sub, XOR, or AND, depending on the func part, ifunc. And for the rest of cases, we always do add, right? Because this ALU will be always used as adder in the other cases. So in summary, if this instruction is OPQ instruction, then actually we do whatever is necessary specified by ifunc, the second field of opcode, ifunc. Otherwise, we always set this ALU instruction to do add. Okay. All right. I'm gonna actually stop here because it's time to announce this homework number 3. So please TA come out and please introduce the homework number 3. Is there any questions about the course, the material I covered? By the way, can everyone come at 11 on next Tuesday on time? I mean, I remember some people actually said they actually had class right before this one, so that they may be late or something like that. Is everyone okay with 11 a.m. Next week? Oh. Oh. 아 정말로? Anyone else? 민방이 아니야. 예비군 훈련서 7일 받은 사람, 7일날 받은 사람. How many? Can you raise up? 둘? 어떡하지? 뭐라고? 동기참을요? 아, 그럼 어떡하지? 좀 생각해봐야 되겠는데. 근데 어차피 뭐 그 주 10일까지 안 되는 거잖아요. 그러면 뭔가 다른 방법을 좀 강구해봐야 되겠는데. 어차피 그날은 못 보는 거네. 알겠어요. 나중에 근데 제출은 하세요. 그 혹시 뭐 준비 시험 보시면 저희가 좀 그 불이익이 없도록 할게요. 한 가지 방법은 아니 불참이 아니라 기말고사 몰빵. 기말고사 75%. 75%. 한 가지 방법. 아니 모르겠어요. 사실 그 외에 다른 방법이 잘 생각이 안 나는데. 국가의 부르심을 받아서 가는 건 뭔가 좀 불이익이 없게 해야죠. 또 다른 질문? Any other questions about the materials or midterm or anything else? Okay. So now it's time.
Hello everyone, I am Song Kim and here to introduce our new lab. This is lab and you will learn about the instruction set architecture and its sequential and pipeline implementation by the example of Y8664. So in this lab, you will learn about the design and implementation of a sequential and pipelines processor using Y8664. Since you get familiar with the instruction set itself, you will start by the assembly programming. So you'll write 3 programs in assembly. So after part A, you will, in order to understand the sequential implementation, you will add an additional instruction called IADQ to existing standard implementation of the processor. The last part, part C, is the most complicated part of the lab. We will optimize the performance of the given program. So you will modify either the assembly code of the program and the whole pipeline to make the existing program faster and faster. To do all the tasks, you need a Linux environment with a Flex and Bison installed on it. So thanks to Bacchus, the Martini server administrators, the Martini server already satisfied the condition. You can use the Martini, but it is not necessary to use it. But especially for Mac users, there can be an announced issue like it did on lab 1, so we recommend to use Martini. To start the lab, please download the lab3.tar from ETL. It'll be uploaded soon. Unzip it and change the directory to the scene folder and make the files. So you are ready to start part A. Your task is to write some assembly programs, as I mentioned, and you'll be working on sim/misc folder, and you'll be modifying sum.ys, rsum.ys, and coffee.ys. Those are skeletons of assembly, so you don't have to care about too much details. The exact specification of the meaning of the programs are written in C on the misc/examples.c. So all you have to do is actually to translate the C codes into its assemblies. Once you're done with the programming, you can test by following these command lines. So you make the assemblers and interpreter. So use YAS and YIS to make the assembly code into an object file and run it. So for part B, you will add a additional instruction called iaddQ into existing sequential implementation, and you will modify the .hcr file. It means hardware control language. So, but it is a new language, but I believe that it won't be that hard for to get to use it. You'll be working on sim/folder, and you'll modify seq full.hcl. There is another HCL file called the seq standard.hcl in the folder. And this is the HCL file for the standard implementation of the sequential processor. You will not modify or submit this standard file, but you can use it as a reference for HCL grammar and sequential implementation. Once you add the iaddQ instruction, you can test it by executing simple programs, and you can follow these command lines to test the implementation. And note that this version equals full here. It specifies the compiler to use your version of seqfull.hcl file to compile the simulator. So you can use csim here by your version of implementation. And if you miss it, your compiler will use seq standard.hcl, which means you can also use the existing implementation. So try executing by the existing one and compare with your version of execution. To get the score, you have to verify your sequential simulator by running tests. First, make sure that the simulator was compiled by your version, and you can run the two tests called benchmark and regression test. Both are meaningful for the score. And for the benchmark programs, please follow those command lines. And for the regression test, please follow those command lines. Please check that this tflex equals I means that you'll be test the whole sequential implementation, including iaddQ. If you miss it, you can only test the previously existing instructions. The last part C, is the highlight of the lab, and your task is to optimize ncopy program. You will either modify the ncopy.ys assembly code directly or the pipeline structure of the implementation. So again, in the folder, you have another HCL parts called standard one and the broken one. Here, the pipe broken.hcl is the almost same to the standard implementation, but it doesn't control any hazard. The hazard was not introduced in the class yet, but you will learn about it soon. So you can refer to these files for, again, for the HCL grammar and the pipeline implementation. To test ncopy.ys and pipeline the simulator, you can test those files independently. So you can test ncopy.ys using standard one of pipeline simulator. If you use it, you will not be disturbed by the your implementation of pipeline simulator. Again, to test your pipeline simulator, do not miss version equals full, and you can test the simulator by executing psim. But to get the score, again, you have to verify the pipeline simulator and ncopy. But ncopy.ys is already verified by the correctness.pl here. So all you have to do more is to execute benchmark tests and regression tests, just like it did on part B. And please follow those comment lines. So once you're done with the correctness, you can check the performance of the ncopy. There are various helpers in the folder, sDriver, AirDriver, checklamp here, but I will not explain all of those files, but please check arclab.pdf or readme to check usage of those files. And the score will be given by benchmark.pl. And I should emphasize that loop unrolling will be helpful for your performance gains. Please find it on the textbook. So those were the tasks, and I will explain how to submit it. We, considering the midterm schedule, we have two due dates. One is for part A and B, and one is part for C. So for part A and B, you have 2 weeks to do it, but for part C, you have one more additional week. But I recommend to start the part C earlier, because it won't be enough to be done in 1 week. For the 2 due dates, the cutoff date and grace dates will be applied independently, so please keep this in mind. For each due dates, you have to submit different parts, lab 3-1.tar and lab 3-2.tar. All you have to submit is your modified files specified on each folders here. So for part A and B, zip it into one tar file, lab 3-1tar, and submit it. Same for the lab 3-2.tar. And for grading policy, please be careful, because it does influence on your score twice much as compared to other labs. So it means that it was 2/5 of your assignment score, because we have one more lab left after this lab. For those policies listed on each part, because time is running out, I'll skip those explanations. Please check arclab.pdf for more details. And granting policy for late submissions and plagiarism, it was already described on introduction of lab 1, so I'll skip this. But please keep those in mind. This ends the presentation, and thanks for paying attention. Any questions?